All right, in this section, we're going to look at linear transformations. Now, I just want to review a little bit of what we've done before. All of Chapter 1 so far, from Section 1.1 to 1.7, looked at basically the same type of systems. We looked at a system of linear equations, so we had a bunch of linear equations. We looked at a vector equation, and we looked at a matrix equation. And we saw that all of these were equivalent in the sense that you could write one as the other, and they're all going to have the same solution set. Okay, and that solution set is going to be some vector of length something or other. Okay, the way I've drawn it here, it would have to be length n. So we looked at different solution sets, but the main issue was solving either the matrix equation or the vector equation or the system of linear equations. And so we were looking at matrices as a rewrite of these first two. We were looking at the matrix equation as sort of a rewrite of the vector equation or a rewrite of the system of linear equations. Now, what we're going to do in this section and in the next is we're going to think of matrix multiplying a vector as like a function. All right? So think of the matrix equation AX equals B. This means A multiplies the vector X and gets out a vector B. Now that's the same thing as what a function does. A function, we input some sort of a number or a variable, and we get out another number or variable. Okay? Now we can use our inputs instead of normally when you see function notation, you think of it as in basic algebra where you're inputting single numbers and getting out single numbers. But we can input vectors and get out vectors as well. So we can associate this matrix multiplying a vector as being just like a function when we input a vector. All right, so we think of our x's as our inputs and our b's as our outputs, the way I've written this matrix equation. And thinking about function notations on vectors, that gives rise to the word transformation. All right, a transformation is just a mapping or a function. We'll call it capital T usually in this class, from one set of vectors to another set of vectors. These could be the same sets, but from one set of vectors to another set of vectors, and where we have each input gives us some output. All right. So a transformation is basically just like a function where our inputs are vectors and our outputs are vectors. Okay. So that's all the word transformation means. Now, as far as the notation goes, let me scroll back just a second. Notice this was a transformation from Rn, so vectors of size n, to vectors of size m. So if we're going from n to m size vectors, the notation we'll say is this. This is the shorthand way of writing it, this middle thing. We say T takes input vectors, which have n entries, and gives you out output vectors, which have m entries. The input vectors are called the domain. The output vectors are called the codomain. The range So the difference between the codomain and the range is sometimes you don't get every vector over here. And so the range is the set of vectors that are actually the outputs. And the outputs are what we call the images. So the output is also known as the image of x. So t of x is the image of x. Again, x is our input, t of x is our output. All right, so in transformation language, we call that the image of x. And if you look at the set of all images, that's called the range. Okay, again, the distinction between range and codomain is all the set of vectors which are have m entries. The range is those vectors which you can map something to. So that's the notation, that's the language we're going to use when we talk about transformations. Now the first type of transformation is going to be a matrix transformation. All right? Basically, this is a transformation defined by letting our transformation, the image of x, be obtained by just taking a matrix times x. All right? And the way we phrase that was we say we define the transformation T by when you input an x, the way to calculate the image is to take the matrix A and multiply by x. All right? So if that's the case, if our transformation is defined by some sort of a matrix multiplication, then we call T a matrix transformation. All right, so a matrix transformation is a transformation that is defined using matrix multiplication. All right, so let's take an example here. We're going to use the notation and the language we have already used. So this says find the image of V under the transformation defined by T of x equals A times x, where that's our A and that's our V. So in order to do this, what we're going to need to do is basically understand what the image means, how we define this. And so let me write that down on a Word document. Click on I clicked on my Word document so you can see it a little bit better. So what's happening here, if we find the image of V under the transformation, what it's actually asking us to do is to find T of V, which we know is going to be what you get when you multiply matrix A times vector V. So all we need to do to find the image of B is multiply matrix A times vector B. Can't get that to bold for some reason. That's better. And then that will be the image. So let's go ahead and do that. Let's take my matrix A and my vector V and multiply them. So multiply these. Hopefully you remember how to do this, how to multiply a matrix times a vector. We're going to take the first column, multiply it by 4, the second column, multiply it by 3, the third column, multiply it by 5, and then add those things up. So we get 4, this will take a while to pull up, times the vector 2, 1, plus 3 times the vector 1, 1, plus 5 times the vector negative 2, 1. Oops, hit the wrong button. And that's giving us, so 4 times 2 plus 3 times 1 plus 5 times negative 2, I believe gives you 5 for the first entry. You can, or excuse me, no, I threw that off. I apologize. 4 times 2 plus 3 times 1 plus 5 times negative 2 gives me 1 as the first entry. So let me write that down. So then 4 times 1 plus 3 times 1 plus 5 times 1 gives me 12 for the second entry. Hopefully I calculated all that right. And so what we're saying is that this vector 1, 2 is the image of the vector v after it's been put into our transformation. So another way to write this in the transformation language would be to say, well, the transformation when I plug in this vector 4, 3, 5, is going to give me out the vector 1, 2. All right, so your input vector is the vector 4, 3, 5. Your output vector is the vector 1, 2. Now in this case, I gave you the A and I gave you the input vector. All right, in the next question, so in this question, sorry, we're going to do the reverse. We're going to give you an output vector and ask, well, what was the input vector I would have needed to multiply by A in order to get out the vector B? Okay, so the way you could phrase this is find an X whose image under T is B. So we're going to take T of X equals A times X again. And again, this time we're looking for the X whose image is B. All right, so there we go. You've probably guessed how we do this. Basically, if my transformation is defined by taking A and multiplying it times a vector and getting out another vector, well, that means that we're really solving this matrix equation. Okay, so we're solving AX equals B, and what that's going to do, that's going to require us to create an augmented matrix, row reduce it, put it in row reduced echelon form. Oops, I need another column. So we're going to create this augmented matrix 2, 1, negative 2, and then 5 for the first row. For the second row, we get 1, 1, 1, 3. Let me not make those letters bold, or those, excuse me, numbers bold. Okay. Put that thing in row reduced echelon form, and we hope that there is, in fact, a solution. We hope that we can actually find a solution. It doesn't give us the no solution case. In this case, we're lucky that it does. Okay, in fact, in this case, when you row reduce it, you'll see that we have a free variable, and that'll lead to infinitely many solutions. Now, just so I have at least one example in this video where I actually went through the row reduced echelon form technique as far as doing it on our calculator goes, I will do this one on my calculator or on the calculator screen. So what we're going to do, as always, go into the matrix menu, edit matrix A, or choose whatever matrix you want. I'm going to use matrix A. I've already have my matrix that I want put in here. It's going to be 2 rows and 4 columns. It's going to be a 2 by 4 matrix. And this is the augmented matrix for that system. 2, 1, negative 2, 5, 1, 1, 1, 3. And then we go back, second quit. Let's go back to the home screen first. And then go up to row reduced echelon form. Again, matrix menu, math. So math is up there. Row reduced echelon form is B. We want to row reduced echelon form. I want to row reduced echelon form matrix A. So just hit enter. And that's what you get. Okay, 1, 0, negative 3, 2, 0, 1, 4, 1. So 1, 0, negative 3, 2, 0, 1, 4, 1. Again, this is the augmented matrix. So we have to imagine our equal sign being right there. If you write that down, well, let me write down the augmented matrix just to start out with. So we write down 1, 0, negative 3, something like that. So here's our augmented matrix. What does that mean? Well, the general solution would say x1 would be equal to 3x3 plus 2. It would also say x2 is equal to negative 4x3 plus 1, and x3 would be free. Okay. Oh, everything's coming up bold. Weird. All right. So that's what it would say. Again, normally the equation's here. That negative 3x3, I'm just adding 3x3 to both sides, moving it over. That's how I'm getting this equation. Okay. Now, notice there are infinitely many solutions that work. If you wanted to write the parametric form for this, the parametric form for this would have 3 entries, right? An x1, an x2, and an x3. So we could call 1 as our x3. If I let 1 be the coefficient of x3, my parametric form would look like 3, negative 4, 1 times any x3 plus the vector 2, 1, 0. Oops. My apologies there. So that would be the parametric form, okay? Now, if I go back to the actual question, it says find an x whose image under T is B. So clearly we found one x. In fact, we found an infinite family of such x's. But one vector whose image is vector B is the vector. Well, plug in any number you want for x3. An easy one would be 0. If I plugged in 0, If you plugged in 0 for x3, you're going to get 2, 1, 0 as the vector you're looking at. 2, 1, 0. Another vector you could have done, you could have plugged in, let's say, 1 for x3. If you'd have plugged in 1, you would have gotten the vector 5, -3, 1. So you could have also used, there we go. What did I say? 5, -3, 1. By the way, you could have also plugged in 2 for x3, or 3 for x3, or 4 for x3, or -1, or -2, or -0.5, right? You could have plugged in any number for x3 you want, and that would have given you a vector whose image is b. Okay, the b we were talking about earlier. Does that make sense? So you could go on and on and on, just plug in different values for x3, and you get different vectors that all give you the image of b. Now, a lot of times, because we get these infinite solution cases, instead of asking ourselves, find a specific vector whose image is b, what we can ask is this vector w in the range of t? Okay, that means, does the matrix equation ax equals w have a solution? All right, remember the range of t was the set of all output vectors. So is w one of the output vectors for our transformation? Now we're going to solve it in the exact same way that we solved the previous problem. We're going to create ax equals w and try to solve the matrix equation. Hopefully, well, either way, if it has a solution, we say that. If it has a solution, then w must be one of the images. If it does not have a solution, then w must not be one of the images. All right, so let's go ahead and do that. I'm going to click on the Word document that we have. I want you to pause the video and try to solve this yourself. I want you to push pause on this video, try to solve it yourself, and then I will click on and show you how it's done. All right, hopefully you went ahead and did that. So basic idea is the basic idea we always do when we solve an equation. We're saying, is w an image? So is it in the range? Is it an image of the matrix A? Which means, can we find an x so that A times x equals w? So we're solving ax equals w. We're going to create the augmented matrix here. Again, remember this is an equal sign. We row reduce echelon form that. And this augmented matrix row reduces to this one, 1, 0, 2, 0, 1, -3. That does have a solution. In fact, what the solution is that x1 has to be 2 and x2 has to be -3. All right, in the general form. In the parametric form, it is just the vector 2, -3. Okay, so in the parametric form, we could have written this as just 2, -3. Now, it doesn't matter that what the solution is in order to answer the problem. So just as long as it has a solution, I don't really care what it is, but this has a solution. Therefore, W is in the range of the transformation. All right. So that's all we really need, that it has a solution. It may have infinitely many in some cases. In fact, in our last case, we saw an infinitely many case. B, we could rephrase that question. We could have said, is B in the range? And we could have said, yes, it is, because there is a solution to that matrix equation, and therefore we can find a vector which maps on to B. Just like this one, we found a vector which maps onto W. So I want you to go ahead, now that you've done that, try this one on your own. We're just going to change that W from what we had to now the vector 7, -23, -5. Go ahead and push pause on the video and do that problem. All right, so hopefully you went ahead and did that. And we'll continue. Let me do this on this page. So we have this A, we have that W. I'm used to saying B, but that's W. We're saying, is W in the range? That means, can I find an X where I multiply it times A and I get W? So solving for X means creating this augmented matrix, 4, 1, 7, -3, 4, -23, 2, 2, -5, and then putting that in row-reduced echelon form. When you put that in row-reduced echelon form, what's going to happen is that bottom row is going to represent the 0 equals 1 thing, right? So we get 0 as our coefficients for x1 and x2 equals 1. So 0 equals 1, which just means that there is no solution to this matrix equation up here. So we cannot find an x which is going to make this matrix equation true. So since we can't find such an x, W is not in the range of the transformation defined by A. So it's not in the range in this case because we got a no solution in our example. Hopefully that all makes sense. So that's the type of questions that we could ask about a matrix transformation. Now, I want to focus on why we were dealing with matrices. And what makes matrices special is these two nice properties that we've seen before. Specifically, that matrix multiplication distributes over addition, and matrix multiplication, I say matrix multiplication multiplied times vectors, obviously, distributes over addition. Matrix multiplication with a vector, we can take a scalar number, any real number, and we can put it inside or outside. So we have the distributive property over vector addition, and we have an associative property over scalar multiplication. Now, if you think about this, what this matrix is doing is it is preserving the addition, okay? It's, in some senses, preserving the addition. And you could say, well, you could do this thing and then add, or you could add, then do this thing. And in some sense, it is preserving scalar multiplication. So I'm going to use those words preserve uh, kind of loosely, but you get the point that it's working nicely with vector addition and it's working nicely with scalar multiplication. Now that means that matrix transformations are a special type of transformation. Matrix transformations are linear transformations, okay? In that a transformation is linear if it has these two properties. If we can sort of preserve addition, in other words, addition before the transformation is going to be equivalent to addition after the transformation. And it preserves scalar multiplication. So scalar multiplication of a vector before the transformation hits is the same as scalar multiplication of a vector after the transformation hits, okay? And it's pretty obvious that all of the matrix transformations are linear. Now, if you think about what's happening here, it's preserving additions and it's preserving scalar multiplications, all right? And so what linear transformations do is they preserve the linear combinations of vectors. Okay, so you could put these two properties together and write a linear combination of u and v, and that would look like a linear combination of their images. All right, I'm not, actually, let's go ahead and do that. What I'm trying to say is if I write out a vector as a linear combination of u1, u2, and u3, and then I hit that with a transformation. Well, because I can sort of factor out scalars, and because my transformation will distribute to each vector individually if I want it to, we're going to get the same result as if we had a linear combination, in fact, the exact same linear combination of the images of those vectors. All right, so linear transformations preserve linear combinations. Linear. All right. Linear transformations are going to preserve linear combinations. Now, I know also we haven't talked about the graphical ideas yet. We are going to do some of that once we get into chapter 4. But if you were thinking about what this looked like on a graph, it turns out linear transformations preserve lines on a graph. So if I have a line on a graph and then I transform it, it's still going to look like a line, but probably pointed in a different direction. Okay, so we preserve lines. We preserve linear combinations. Now, a good question to ask is, if we define a transformation, how can we tell if it's linear or if it's not? So let's try to determine if the following transformation is linear. So here's what our transformation is going to do. It's going to take a vector from R3, a three-dimensional vector, which is arbitrary. We'll call it x1, x2, x3. So it'll take any vector that looks like this, and it's going to spit out in a two-dimensional vector, a vector in R2, with 5 as the first entry and x1 plus 3x2 as the second entry. Okay? Now we're going to try to see if this is linear. But before we do that, let's just take a second to think about what this transformation is actually doing for you. All right, so let's go to this, and let's plug in just a couple of arbitrary vectors. Let's plug in 2, 4, 6. So 2 is the first entry, 4 is the second, and 6 is the third entry. So plug that in into the transformation. What are we going to get out? Well, the first entry of our two-dimensional vector, the first entry of the output is going to have to be 5. The second entry is going to be what you get when you plug in 2 into the x1 spot and 4 into the x2 spot. So 2 plus 3 times 4. Let me just write that. So we've plugged in 2 into the x1 spot and 4 into the x2 spot. 2 plus 3 times 4 is 14. Double check that. So we get out 514. All right. What if we plug in some other vector? Let's say we plugged in the 0 vector. So if I plug in the 0 vector, what am I going to get? 0, 0, 0. Plug that in. My first entry is going to be 5. My second entry is going to be 0 plus 3 times 0. Obviously, 0 plus 3 times 0 is just all 0. So when you plug in the 0 vector, you get out the vector 5, 0. Okay, so that's what that transformation's doing. Hopefully that all makes sense. Now the question is, does this preserve addition? And does this preserve scalar multiplication? Okay? Now we can test the addition and show that it doesn't hold just based on these two vectors themselves. Think about what would happen if you added these two vectors before you applied the transformation. So you add these two vectors before you apply the transformation. If I add them first, you're just going to get, well, what we had before. You're going to end up with 2, 4, 6. Again, I'm adding these and then applying the transformation, which we know is 514. Now, if you take and you added the two vectors after you applied the transformation, well, what would you get? You get 514 as the outcome of this one, and you would get 50, whoops, as the outcome of the other one. Notice that when you add those two up after you did the linear transformation, you end up with a 10 in the first spot and a 14 in the second spot. So this must not have been linear. This transformation is not a linear transformation because you get different answers depending on whether you added up before you took the transformation or whether you added up after you took the transformation. So this transformation is not linear, okay? And really, that first entry of the 5 was the problem, okay? That first entry of the 5 was the issue. Now, one of the observations that's going to clearly come out of this is that in order to be linear, your transformation is going to have to let the 0 vector go to 0. All right? So again, these might not be the same dimensions. This might be a 3-dimensional 0 vector, so a 0 vector with 3 entries, and this might be a 0 vector with 2 entries. But in order to be linear, we have to let the 0 vector go to 0. Okay, the transformation has to do that. Otherwise, we're stuck in a situation where if it doesn't go to 0, we're stuck in a situation like this. If this is not the 0 vector, adding a 0 vector, well, how do I say this? Let me do this more general. Let me write it more generally. So because of that property, if you add the 0 vector to any vector v, you're going to get out the vector v. Okay? Now, in order for a transformation to be linear, a linear transformation has to have this t of v plus 0 be equal to t of v plus t of 0. Okay? So those two things have to be equal in order for, this to be linear. So t of v plus 0 has to be equal to t of v plus t of 0, which, again, if you focus on this equation, so in order to be linear, this t of z can't add anything to this one. This t of 0 cannot add anything to this one here. Okay, so subtracting t of v from both sides, we get that the 0 vector has to be t of 0. Hopefully that's not too arbitrary, but that's what's happening. Again, if you want to do this line by line, you'd say, well, to be linear, we have to have this property. But the left-hand side of that equation, I can simplify because I know a vector plus the 0 vector is just itself. And then I can simplify that equation again by subtracting t of v from both sides. So I'd subtract t of v, subtract t of v. And that's giving me that 0 is equal to t of 0. Hopefully that makes sense. All right. So in order to be linear, we have to have this. Not just with the 0 vector, but with any vector, we have to have that. but in particular with the 0 vector, we have to have that. So subtract t of v from both sides. It forces the 0 vector to be transformed into the 0 vector. So in order to be linear, the 0 vector has to be transformed into the 0 vector. Again, like I said, this may be a three-dimensional 0 vector to a two-dimensional 0 vector, but or vice versa, but it's still 0 vector to 0 vector. Now let's do the next transformation. Let's try to determine if this transformation is linear. Now, I'm going to spoil the whole thing. It's going to be linear, all right? If you plug in the zero, well, first off, the only observation that we know so far, if I plug in the 0 vector, it does in fact give me 0, all right? But how would I show that this transformation is linear? Well, what I would have to done is show that the two properties of linearity work. So I'd show that it preserves addition, and I would show that this transformation also preserves scalar multiplication. So I'm going to go ahead and do that. All right, so let's go ahead and do that like I said. Now, one thing that we have to note here, let's take this first property. First off, here's our transformation. Okay, our transformation takes x1, x2, x3 to 4x3, 6x2. We want to show that this property holds for any u and any v that you can think of. All right? There's a couple of different approaches. Some people like to plug in an arbitrary u and an arbitrary v into this one, and then simplify it, and then plug in the same arbitrary u and the same arbitrary v into this one, and then simplify it, and show that the two sides are equal. Other times, people will plug in an arbitrary u and an arbitrary v into this one, and then using like algebraic techniques, just show that that had to be equal in one big long, this is equal to that, is equal to that, is equal to that, and then finally come up with a u, t of u, and t of v at the end. Okay, that's the approach I'm going to take. Again, there's sort of a one long approach or a two-sided approach. They're basically the same thing. Okay, so I know that sounds a little bit crazy, but let's do this. So let's plug in an arbitrary u and an arbitrary v. And I will start with the left-hand side of that equation. So if I plug in an arbitrary u, what I can do is I can pretend this is u1, u2, u3 as the vector u, and an arbitrary vector v we could write as v1, v2, v3. Now the left-hand side wants me to add these things before. It's kind of bad notation because I used vectors for v1, v2, v3 a lot, but now v1, v2, v3 are standing for real numbers. But it doesn't really change what's happening. Okay, so let's start simplifying that. Now, the left-hand side says add first. So what we're going to do is we're going to add these two things, and we're going to get one big, ugly vector. All right? So we're going to get t of a vector, and oops, that vector is going to have three entries, the first of which is going to be the number u1 plus the number v1. The second entry is going to be the number U2 plus the number V2. The third entry is going to be the number U3 plus the number V3. All right. Those are just real numbers, so we're not going to bold those. Now, here's where the transformation comes into play. The transformation is supposed to do this thing. All right. So if I plug in a three-dimensional vector, I'm supposed to get out 4 times that third entry in the first spot of my vector, of my output vector, and 6 times the second entry in the second spot of my image, or again, output vector. So what is that? How does that translate, to here? Well, what you're going to get out is 4 times this third entry, so 4 multiplied times the number U3 plus V3. Notice that because we're multiplying the entire third entry, that entire third entry needs to be in parentheses. And then this second entry of my output vector, the second entry of my image, will be 6 times the second entry. Well, in this case, 6 times the second entry is 6 times U2 plus V2. All right. Since these are all real numbers, I'm going to unbold them. Keeps doing that. See if this will do it. And if you wanted to, you can look at what's going to happen. So your final answer when you distribute the 4 is going to be 4 times U3 plus 4 times V3 in the first entry, and then 6 times U2 plus 6 times V2 in the second entry. All right, so that's going to be the outcome. Now, like I said, at this point, there's kind of 2 methods to this. Here's our outcome. What I could do now is stop and do the exact same thing for the right-hand side of the equation. All right. Or I could keep going and try to use algebra to force this to look like the right-hand side of the equation. Let me start by doing the first thing I said. So let's start. So here's our output of what happens when we add first and then apply the transformation. Now let's go back and kind of start over and figure out what the output would be if we did the transformation first and then added. All right, so if we did the transformation first and then added, well, what would we be doing? We'd be taking an arbitrary u, applying the transformation, and then adding it to an arbitrary v in which we applied the transformation. Now, if we did that, again, our transformation tells us that we're going to create a two-dimensional vector, a vector from R2, which takes 4 times the third entry and then 6 times the second entry. So our output, if I apply the t first, is going to be, 4 times the third entry of u, 6 times the second entry of u. That'll be the output you get from this piece, and then we're going to add the output you get from this piece. Now the output you get from that piece, whoops, the output that you get from that piece is going to be another two-dimensional vector. It is going to be 4 times v3, 6 times v2, notice what's going to happen if we add those two things up. If you add these two things up, what you could have gotten, or what you would have gotten, is 4 times u3 plus 4 times v3. Whoops. In the first entry, and 6 times u2 plus 6 times v2 in the second entry. So you see that no matter what the vectors, since this u plus v and then apply the transformation leads to the same result as u plus v after you've applied the transformation to each one. Since you get the same thing in both cases, now we know this property will hold for all u and all v, because I did it for arbitrary u and an arbitrary v. So holds for all u and v's, u's and v's. Okay. Oh, I bolded that, but that's okay. So that property holds. Okay. Now, this is sort of the two directional pathways where you kind of meet in the middle. All right, so you go two directions. You start with the left-hand side, you simplify that. Then you go with the right-hand side, you simplify that, and you meet in the middle. You could have also done something like this. You could have kind of combined the two, and this is what I was trying to get at before, to say, well, let's start with the left-hand side. You go to this point, and once you get to this point, you start breaking things up. All right, so you start breaking things up and sort of factoring them, if you will. You could have factored that single vector into a sum of two different vectors for u3, 6, u2, and then for v3, whoops, for v3, dang it, I forgot to put two entries in there, 4v3, 6v2. So the other method is to do that, and then notice that this first vector here let me do this, let me take it, there you go. First vector is your image of an arbitrary u. Your second vector is an image of an arbitrary v. So you got this t of u plus v is equal eventually to t of u plus t of v. All right, that was a little bit longer than I thought. So you could do this sort of technique where you start with this side and you simplify it till you get a vector, and then you start with this side and you simplify till you get a vector, and if it's linear, these vectors will be the same. Or you could start with this side, simplify it, and then sort of break it apart again until you get to these two vectors. All right. So either way is okay. Just as long as you take arbitrary numbers in your entries, that will show that t of u plus v is equal to t of u plus t of v for all the vectors we want. Okay. Now, that took a long time, but that was just one of the properties. Okay. The other property that we need to show is that it's preserved under scalar multiplication. So we also want to show that if you take a scalar times an arbitrary vector, it wouldn't matter if you did that scalar multiplication before or after you applied the transformation. Okay, so once again, we're using this transformation here, and we're just going to use an arbitrary vector. I'm going to copy that over so I don't have to write as much. So what we do, just like before, is we create an arbitrary u. Now, our arbitrary u has to be 3 dimensions because that's the input of our transformations. We're going to multiply that times an arbitrary real number, which we call c. Inside, now if you think about what that would be, that is going to give you, excuse me, c times u1, c times u2, c times u3 inside the transformation. Once you apply the transformation, again, we're using the same transformation, so our outputs are going to be 2 by 2 vectors. And if you remember, or sorry, not 2 by 2, 2 by 1 vectors, 2 rows, 1 column. We're going to get the result by taking 4 times the third entry and then 6 times the second entry. So 4 times the third entry is that. 6 times the second entry is that. And that's what we end up with. Now, just like the previous problem, if you want to, you can kind of break this apart. You can keep writing equal and then break this apart until you get something that looks like that. Or you could start with another line and put c times t times some arbitrary u and try to simplify it until the ending product looks like that. All right, either way is fine. What I'm going to do is I'm going to keep going with this. So if you keep going with this, what I can do is I can factor out a c, and then in the vector, what would be left is 4 times u3, 6 times u2, which is just a constant multiplied times the image of that arbitrary vector u. Okay, so again, this is the one line approach. So this is equal to that is equal to that. Let's break it apart and get there. And since this thing is equal to this thing, so multiplying by the scalar before is the same as multiplying by the scalar after, this holds true for all u's and all scalars. All right, so our transformation, that was a long time, but worth it. Our transformation was linear because both of those properties held for any vectors that we could think of. So any arbitrary vectors, u and v, that we could think of, the two properties of linearity held. Okay? Now let's go to this one. All right, we're going to determine if the following transformation is linear. Now, you probably, once you look at this transformation and you understand what the word linear actually means, red flags should go off when you square something, right? Linear has something to do with lines. Linear equations all have our variables to the first power. So there should be red flags going off when we square things. And rightly so. This transformation is in fact not linear. Now, to show that it's not linear, we just have to show that one of the properties holds for some vectors or some scalars, right? So we just need to show that there's one vector where, let me say it this way, we have two properties to show linearity, okay? If either of those don't hold, then our transformation's not linear. So we need to focus on one property and show that it doesn't hold at some spot. So what we're going to do is we're going to pick one of our properties. In fact, it doesn't matter which one you pick. It's kind of, this transformation won't hold for either property. But let me pick this property here. Okay, let's pick the scalar multiple property. I claim that there are certain vectors out there that this scalar multiple property will not hold for. All right, so all we have to do, we don't have to have an arbitrary u in this case to show it doesn't hold. We can show that it doesn't hold on some u. So all we have to do is find a scalar and a vector which we don't, which our property doesn't hold. Now let's go 5, 5, 5. Whoops, 5, 5, 5. With a scalar of 3. All right. Now let's multiply the 3 first and then do the transformation. So if I multiply the 3 first, I'm ending up with 15, 15, 15. If I do the transformation, my output is going to be a two-dimensional vector. This is kind of easy because my third entry is going to be squared. So if I square that third entry, I get 225. If I just take the second entry by itself, I'm ending up with 15. All right. So if you put 5, 5, 5 in as your vector, and you put 3 in as your scalar, and you multiply your scalar times your vector before the transformation, you get this. Now what's going to happen if we multiply the scalar times the vector after the transformation? Excuse me. So if we multiply the scalar times the vector I get after I do the transformation, 3 times this. Well, the transformation, first, let's do this. We have to square the third value. So square the third value, square 5. If you square 5, you get 25. So square 5, you get 25. Take x2, again, that's a 5, and that's all that is there. So we get 25, 5 after you apply the transformation, and then we're going to multiply that by 3 afterwards. And very easily, you'll see that these two vectors are not the same because that first entry is different. So multiplying by a 3 before you take the transformation gives you a different answer than multiplying by the 3 after the transformation. Therefore, this equation cannot be true for all U and C. So that equation is not true, and therefore our transformation is not linear. Okay, so the transformation and again, that was fairly straightforward. That's what we probably thought based on having a square. Again, if we know anything about the word linear and squaring things don't match up. Linear and squaring variables is a bad combination. All right. Now, I want you to see if this next transformation is a linear transformation or not. Okay. It's a little bit messier. It's still taking a 3-entry vector and spitting out a 2-entry vector, but our 2 entries are linear combinations of the entries over here. So our 2 vectors are going to be, or 2 entries are going to be linear combinations of the entries of the vector I plug in. All right. Push pause on the video and see if both of those properties can hold for an arbitrary u and arbitrary v, an arbitrary constant. So hopefully you push pause and went ahead and did that. It's kind of a long process. It's not a hard algebraic process, but it does take a little bit of time. But you can show that in fact this is a linear transformation. Put in an arbitrary u, arbitrary v, arbitrary constant, and you'll see that the 2 properties of linearity actually hold. All right. So let's go ahead and do that. So I'm going to start with this first property. We're going to see if this first property holds. We're going to put in an arbitrary u and an arbitrary v. Now, the u and the v have to be from R3. They have to be 3-dimensional. They have to have 3 entries because that's what we're given. We're given that we start with a vector with 3 entries and we get an output which is a vector with 2 entries. So the arbitrary u, I'm going to call u1, u2, u3. The arbitrary v, I'm going to call v1, v2, v3. Now I'm going to take the approach of adding first and then taking the transformation and then simplifying as much as possible and then putting a u into the transformation, putting a v into the transformation, then adding and then simplifying as much as possible. And hopefully we can see clearly that for an arbitrary u and v, that the two sides of this equation must be equal. All right, so if I'm doing that, excuse me, first I would add the two vectors. If I add the two vectors, the first entry is going to be u1 plus v1. The second entry is going to be u2 plus v2. The third entry is going to be u3 plus v3. Okay, so that's what we get when we add the two arbitrary vectors. Now I want to apply this transformation. Notice what the transformation does. It goes 4 times my second entry minus 7 times my third entry. That is going to be the top spot of our image. Now, it's a little bit difficult because this second entry is not just a single number here, it's a sum of u2 and v2. So you're going to do 4 times the number u2 plus v2 minus 7 times the number u3 plus v3. So that's going to be whatever you get out. Again, it's going to be some sort of number. Whatever that number is, that is going to be the first entry of your image, the first entry of the output vector. Now x1, first entry, so excuse me, the first entry of the output vector is going to look like that. First entry of the image is going to look like that. Second entry of the image looks like this. You took your first spot of your input plus 3 times your second spot on your input. So first spot on my input is u1 plus plus v1, u1 plus v1. And then the second spot on my input is going to be u2 plus v2. So we get a vector as an output that looks like this. Now I'm going to simplify that real quick, and the only thing I'm really going to do is distribute the 4 into both spots and distribute the negative into both spots of the first entry, and of the second entry I'm just going to get rid of these parentheses, they're not needed, and distribute that 3 in. Okay, so hopefully makes sense. If I distribute the 4 in, oh, it's going to give me 4 u2 plus 4 v2 minus 7 u3 minus 7 v3. That'll be my first entry. My second entry of my image is going to be u1 plus v1 plus 3 times u2 plus 3 times v2. And that's about as simple as I can make that. All right, so that's as simple as I can make that. Again, it's fairly long, but pretty straightforward. A lot of algebra, but nothing really difficult. No one part too difficult. All right, so this is the output I get when we add first and then transform. Hopefully, we're going to get that same output when we transform first and then add. So let's go ahead and transform first and then add. So transform the arbitrary u, you end up with 4 times u2. In fact, I am just going to go 4 times u2 minus 7 times u3. And then my second entry of the u's is going to be u1 plus 3 times u2. Again, that's just from the definition of what the transformation does to an arbitrary vector. Similarly, with the v's, when we transform it, you get it 4 v2 minus 7 v3, and then you get an x1, not an x1, a v1 plus 3 v2. Okay? Now, if you add those two vectors together, what vector are we getting out? Well, we're getting out the vector that we wanted to. You can kind of reorder things if you'd like, but you're going to end up, you can see, hopefully you can see, you're going to end up with the exact same vector 4u2 plus 4v2 minus 7u3 minus 7v3, u1 plus v1 plus 3u2 plus 3v2, excuse me. So you get the exact same vector either way, and therefore since you used an arbitrary u and an arbitrary v, this equation is true for all u and all v. Okay? So that equation is true. Now for the other, so that's just one property. If I have to show that the other property holds true, I'll do this on a new page. The other property was taking a constant times an arbitrary vector before and after you'll apply the transformation and seeing that it works. All right, so if I apply the constant multiplication first, I'm going to end up with taking my transformation of a vector c times u1, c times u2, c times u3. I'm going to write this down fairly quickly, but basically the idea is you now apply the transformation. If you now apply the transformation, it is going to be 4 times the second entry. The second entry is cu2. And then minus 7 times the third entry. Third entry is cu3. Next, we're going to take the first entry, cu1, and add 3 times the second entry, and so my output vector looks like this. If you want to get rid of these parentheses, you can just leave those off. Because we're just multiplying everything there. So that's what you get when you multiply before and then do your transformation. Now let's go ahead and do the transformation first and then multiply. So we take C, whoops, and then what would we get as our output vector? Well, when you take the transformation first, my first entry of the image is going to be 4 times U 2, 4 times the second entry, minus 7 times the third entry. Then I take the first entry and add 3 times the second entry. All right, so transformation first. Well, when you take that transformation and you multiply it times c, hopefully it's pretty obvious that distribute c into this. You'd go 4cu2 minus 7cu3. Distribute c into this one. You'd get cu1 plus 3cu2. And in fact, these give you the same things. So this holds true. This equation holds true. For all vectors and scalars. Right? And because both equations hold true for all vectors and all scalars, that means T is a linear transformation. Now, it's good to go through that by hand once, just so that it reminds us every time that to be a transformation, you have to have these two properties hold. That's what it really means to be a linear transformation. But we can take into our mind now what a linear transformation really has to look like. A linear transformation has to take one vector to another vector. And if you're looking at the inputs, or excuse me, if you're looking at the numbers that form the rows of the image, all right, so if you're looking at the output vector, the entries in the output vector are going to have to be linear combinations of the entries in the input vector. So in order to be linear, the entries in the output vector are going to be linear combinations of the entries in the input vector. And notice when I say entries, this very first one we looked at, that was kind of true. This was almost a linear combination, but this had a constant number here. And so if ever you have a constant number laying around, or if you had like 5 plus x1, because that 5 is not the coefficient of any entry in your input vector, it is not going to be a linear transformation. And so that's the observation I want you to make. It took us a long time to get there, but this is the observation we want to make. If we have a linear transformation, and let's say it starts from R3, so the entry inputs are R3, that means there's 3 inputs. To be a linear transformation, each of the entries in our output vector has to be linear in that it is a linear combination of the entries in your input vector without any constants lying around. So for instance, again, if you did x1 plus x2 plus 5 as one of the entries, that would not be a linear transformation because of the plus 5 part. Hopefully that makes sense. So actually, let me write that down real quick. What I'm saying is if you had a transformation and it was 4x2 minus 1x1 plus 9, that plus 9 would not be allowed for a linear transformation. It would throw off the linear transformation because notice if you plugged in zeros into all your variables, you don't get out the zero vector. So each of these entries has to be linear, and we can't have constants like +9 or +5 laying around. Okay, so this would be a linear transformation. If you added a +9 or a +3, that would not be a linear transformation. And if we did something weird with one of our variables, like took a square, tried to square our variable, that would obviously not be a linear transformation either. Okay. So squaring variables, having constants lying around, doing other things to our variables makes it not linear. So we have to have linear entries without any constants lying around. All right. So to be a linear transformation, it needs to look like that. And then when we go back up and we look at our very original one we dealt with, we say, oh yeah, that can't be, we can immediately say, yes, this can't be linear because of the constant 5 that's there. We say, yes, this one is linear because notice that each entry of my image is a linear combination of the entries in my input vector. This one is not linear, this transformation is not linear because of this first entry. This is not a linear function. And then this is linear because the first entry is a linear function that doesn't involve constants. The second entry is a linear function that doesn't involve constants. All right. So now we can kind of easily depict and easily categorize all the transformations which are linear. All right. Now again, why that's important is because in the next section, we'll see how that works out. And also, the nice thing about linear functions is that those two properties, when I talk about doing transformations of vectors, it's going to preserve lines when we do transformations of vectors. Again, they're going to be skewed and they're going to be all kinds of weird, but a line will map to a line. Hopefully that makes sense. And that is the end of the introduction to linear transformations. We're going to show next time, again, we're going to go back to the matrix transformations and show how they're related to all linear transformations. All right, so we'll see you next video.